Good evening, good evening, good evening, good morning. We are back with another live. I've got my cosmology book ready for you guys. I actually made some notes for you as well earlier today. So I am ready to go with you guys on our discussion for our nightly physics lives, where we have been mostly focused on cosmology topics, including but not limited to the early universe, smooth universe, and perturbations around the smooth universe, although haven't really gotten too much into the perturbations or anisotropies part yet. But we have discussed, of course, the smooth expanding universe, expansion of the universe, evidence of the expansion of the universe, dark energy, dark matter. We have dedicated some time on these live streams on dark matter candidates as well. We have also talked about the distinction between cosmology, astrophysics, astronomy, particle physics, and we've really enjoyed everybody's engaging comments. I'm looking over to my kitty cats, Fuji, Suji, and Baji, who are running around. Oftentimes they have zoomies around this time, so it is actually a very lively period of time for us in the night, and we are happy that you're joining. Thank you so much to everybody who is joining. Thank you so much for your participation ahead of time. Thank you for all the comments that we will be seeing today. Thank you for jumping into the live chat and giving us your love and support, as well as any comments. Hello, welcome. Thank you also. If you are watching this as a video upload later on, please do leave us a comment. Love to see it. And thank you very much for joining. Welcome. And let me share the live before I forget, as per usual. How are you?
You know, people that have their
Oh God. Some other video started. I'm so sorry. That was TikTok, which is apparently going to be banned.
If you have anxiety.
Oh my God. I'm so sorry. There's all kinds of videos starting because I'm trying to get to my YouTube channel. But before that, we must traverse the path of muting everything and making sure that we don't listen to anything that we were not. Oh, hello. Hi, Jesus. Mauricio. Hi, Mauricio. How are you? Hello, everybody. Welcome to the live. Welcome. Let me comment. Welcome, everybody. Thank you for being here. Join us and chat. We're going to be talking about physics and kitty cats very soon here. In fact, we've already started. But join us and chat. Tell us your comments and share with us anything you want to share. And I was going to say hi in the chat. Yes, don't feel shy. You dummy. Okay. Hi, you dummy. How are you? Hello. My new pretend. Okay. Awesome. Thank you for joining. Let me share it before I get too distracted. You know, I am trying to do a thing where I share the live, but then I generally remember it 3 hours later. So give me 1 second. Okay, so this live will have kitty cats as well as me, as well as physics, as well as a discussion on cosmology. So hi. Hello, Rodolfo Robles. Hello. Yes, Rodolfo Robles. I like that name a lot. Thank you, everybody, for being here. Welcome. Okay, so we are getting ready to talk further about cosmology. So we had an extremely engaging live recently where I spoke about cosmology the whole night, and people loved it, and all kinds of awesome cosmologists and universe enthusiasts, at least, were in the live. and contributed a lot to an amazing chat. So I'm hoping for the same sort of thing here today. Please do come in and join us in the live, join us in the chat, and give us your comments and thoughts and participate heavily. Don't feel shy, or just keep on listening to this as you do other things in the background. We don't mind, as long as you're still with us, watching and listening and participating as you wish. So, we have been talking about cosmology. I know this is sort of a kitty cat channel, but we also talk about physics quite heavily on these live streams, especially at night. And a lot of people find this to be very useful discussion, either because they're interested or they fall asleep to this. So, this is sort of a soothing live, if you will, peaceful content. All of that is going to be going on here. A lot of people, have enjoyed it. So we have been talking about cosmology lately. I also talked about pretty much the highlights of the 20th century physics, all of the things that kind of started to come to be in the topics of physics in the 20th century, including but not limited to, of course, relativity, photoelectric effect, or the quantum nature of light, quantum mechanics, all of the different developments of quantum mechanics that were really happening for the first time and coming into being. One second, I actually see a problem in the kitchen. I'll be right back. There is a bowl of water that Fuji is trying to tip over. 1 second. Okay. Hi, Fuji. Don't do that. Okay. All right. Now we're good. Okay. Hello. Hello again. Okay, so does anyone else want to say anything in the chat before we get started with today's topic? And all my notes and books. Welcome. Okay, so we talked about how basically Einstein came up with the theories of special theory of relativity and general theory of relativity in the 20th century. This really led to an immense growth in the field of cosmology. After doing everything, after covering everything that we covered in the 20th century, which of course also gave us quantum mechanics, and from which we developed particle physics and quantum field theory, those topics have seen a lot of development as well. And we have talked about that as well in the live. But now coming to our current century, because that's kind of where we are now, and understanding what types of physics is of interest right now in our current work, it was really good to lay the foundation by covering everything in the 20th century in the last 100 years or so, because it really kind of brings us to this point of right now. So in the right now type of universe, the top questions that are still open and still what we have to answer are really the following: what is dark energy and what is dark matter? Those two are the top open questions of this universe. And so we have been trying to kind of approach those and understand cosmology in the process. We've kind of looked at it in terms of astronomy and astrophysics already, because I also had with me an astrophysics book here on the live, and I gave you guys an overview of dark matter candidates, for example, from an astrophysics point of view. And we looked at that and we saw what they were kind of approaching it as. Then we also talked about how astronomy versus astrophysics versus particle physics versus cosmology are kind of different topics. So right now we are actually in the topic of cosmology, and we have been covering the following types of things. So let me get started. Today I wanted to talk about the Hubble rate. So we know, so today's topic, we're gonna go over some math. So this could be sort of one of those lives that is less popular, but if you're seeing this later on as a video upload, I think you'll find this useful in our overall discussion, because we can't really avoid the math too much when we're doing cosmology. It won't make sense. So let me, excuse me, let me read a little bit from this paragraph right here, which will set the tone for what we're about to do, okay? Einstein's discovery of general relativity in the last century enabled us, for the first time in history, to come up with a compelling, testable theory of the universe. The realization that the universe is expanding and was once much hotter and denser allows us to modernize the deep, age-old questions: why are we here and how did we get here? The updated versions are now: how did the elements form? Why is the universe so smooth? So I'll elaborate a little bit more. So a lot of people might have sort of philosophical questions about why are we here, how did we get here, things like that. But we actually, in cosmology, we can actually approach it in terms of how did the universe get started, and for example, the Big Bang. Hi, Fuji. And what the how the universe has evolved from that time, and how the early universe has left us certain clues that we can find, for example, in the cosmic microwave background, which gives us signatures of a very smooth universe. And for the longest time, we actually thought that this early universe was very, very smooth and very homogeneous, and there was a lack of inhomogeneity or anisotropy. And turns out later on, after about 25 years of staring at this CMB signatures, we might actually see certain anisotropies, and we might actually find certain perturbations. We will get into much more of the math of that or the meaning of that later on in this live, but I'll keep going now. But basically, back when the universe was just getting started, back when we had the Big Bang, sorry about the interruptions, just go with it. Back when the universe was anywhere between a few seconds old to 300,000 years old, basically the universe has evolved a lot. Back then it was radiation dominated. Later on it became more matter dominated, and then also it has been expanding. Turns out we have evidence of this, and we even introduced something called the scale factor, which gives us a way to get the mathematics of this expansion, allow us to define this expansion. So we will keep going from this paragraph just so that we can set the tone here. So remarkably, these questions and many like them have quantitative answers that can be found only by combining our knowledge of fundamental physics with our understanding of the conditions in the early universe. So understanding as far back as we can in the early universe is going to be very important, and this is why something like the cosmic microwave background, which is our measurement of photons from when the universe was only 300,000 years old, is extremely important. So you'll see that sort of thing coming up again and again during our discussions about the universe here in terms of cosmology, which is the study of the universe. Basically, it's a subfield of physics. You will see them talking about the smooth universe or cosmic microwave background radiation. So smooth universe and cosmic, this is kind of related. Basically, we have photons that we have collected from when the universe was pretty young. Because the universe is around 14 billion years old at this time, when it was only 300,000 years old, that's a very young universe or early universe. When we have photons that are as old as that, or photons that are from that young universe, it's a very big deal, and it's been observed for a very long time, has been studied for a very long time. At this point, it's been studied for decades. And so this is called a cosmic microwave background radiation. There is even a temperature associated with it, and that's why we call it microwave. It's kind of the wavelength of it, the temperature of it is associated with microwave. But more than that, after studying it a lot, in the beginning for like 25 years, people thought it was very smooth, very homogeneous looking, very equilibrium-y. And basically that's what people mean by the early smooth universe. That's what they mean, because they're thinking, okay, so where are the inhomogeneities? So photons were king of the jungle when the universe first started, and they were constantly, it was a very hot, dense universe. So you couldn't even form an atom, right? You couldn't really form matter. You couldn't really form things like us. We couldn't even form stars. By the time the first stars are forming later on, and those stars are dying and making elements and spewing gas into space and making galaxies, and all of that stuff is much later. So you and I are coming much later. We're talking at this point in the still the early universe, when pretty much we didn't really even have neutral atoms. So this chapter, this beginning chapter, we have kind of gone over this in a previous live stream already, but I'm just kind of summarizing it for you. This chapter describes the idea of an expanding universe without using the equations of general relativity. So for now, we won't use the equations of general relativity, but later on we will. So this is just a little primer. The success of the Big Bang rests on three observational pillars, the Hubble diagram exhibiting expansion. So Hubble told us that the universe is expanding. Light element abundances which are in accord with Big Bang nucleosynthesis. So we talked about Big Bang nucleosynthesis earlier in a previous live, and we saw that it was pretty much what they were expecting the Big Bang nucleosynthesis to have formed. We kind of have confirmation that that's what was made back then in the Big Bang. And the black body radiation left over from the first few 100,000 years, which is of course the cosmic microwave background, because the universe, just like anything else, can have a black body radiation associated with it. From all the stuff that it did in the first few 100,000 years, there is a black body radiation that's kind of left over that we can get photons from even now. And we have, for many years, we have been collecting that and studying it, and it's called the cosmic microwave background. After introducing these pieces of evidence, the author will move beyond the standard model. By that, he basically means, so in this chapter, we're just kind of summarizing because we've covered this chapter already, but basically he means that dark matter is not something that comes out of the standard model, at least not yet. I mean, not so far. We don't know what dark matter is, and the standard model of particle physics does not give us dark matter. But we have evidence of dark matter, both in astrophysics, we saw that there's evidence of dark matter. We also saw compelling evidence of dark matter in cosmology way as well. So we have another whole set of evidence from this cosmological approach that we also covered in a previous live stream. Developments in the last 2 decades of the 20th century, so the 1980s and 1990s, both theoretical and observational, point to the existence of dark matter and perhaps even dark energy. So these are open questions. We don't know exactly what dark matter is. We need to figure it out. We don't know exactly what dark energy is. We just don't know. We just know that there is something that's making the universe expand, and we call that dark energy. But we don't know exactly what the nature of it is. The need to understand the evolution of perturbations around the zeroth order smooth universe, so that very homogeneous CMB that I was talking about, the cosmic microwave background radiation, when you look at it, it looks very smooth, like it's the same everywhere in the universe. But there are probably some perturbations around the main order or the zeroth order of that thing, and those perturbations are going to be important in our understanding of the universe, and maybe even have clues to things like baryonic matter and dark matter. But I will just say, to shorten our discussion, that we are already established in a previous live stream that dark matter is non-baryonic. The cosmological evidence of dark matter gives us non-baryonic dark matter. It gives us the fact that baryonic matter is only 5% of the content of the universe, and overall matter, total matter, is 30%, so 25% is dark matter. So, something we have to figure out. Inflation, the generator of these perturbations. So that's something we'll get into later. We haven't talked too much about perturbations, so if you're feeling like that's confusing, don't worry about it. We'll get into it later. So, for now, we will just reiterate that the scale factor A is something we've introduced. Its present value is set to 1, but basically the scale factor is given by, we call it small a, and so it is convenient to describe this effect of the universe's expansion, that is, by introducing the scale factor small a, whose present value is set to 1. At earlier times, small a was smaller than it is today. We can picture space as a grid. So it's kind of like little boxes, and then the boxes like a little square, and then the square just gets bigger. And basically, it's because the co-moving distance between these things are getting bigger because of the expansion of the universe. So we will see in the picture here in the book, these little boxes I can show you right here. See right there. Basically that shows this grid, which expands uniformly as time evolves. Points on the grid maintain their coordinates, so the co-moving distance between 2 points with just measures the difference between coordinates remains constant. So, however, the physical distance is proportional to the scale factor. So that's why the scale factor is very important, given by small a. So I wanted to introduce it again today so that you can keep it in mind. And the physical distance does evolve with time. So scale factor evolves with time, small t, which is cosmic time. So you'll see us kind of referencing this relationship between the scale factor small a and cosmic time small t a lot. And actually we've already established, but this is just a summary, that back when the universe was radiation dominated and it was mostly just like photons doing their thing, not letting much else really develop, then back then the small a, the scale factor, was dependent on time as t to the 1/2. But later on, when it became more matter dominated, it actually went from t to the 1/2 ish to t to the 2/3. So by also kind of studying the dependence of small a, or the scale factor, the dependence of it on cosmic time, we can actually tell certain things about how the universe has evolved over time. And if we, say expect a certain time period to have been radiation dominated versus matter dominated versus maybe something else dominated, we can even track this and see, oh, something else happened. The content of the universe has changed, and that's reflected in this dependence of the scale factor on the time. So there's various ways in cosmology to kind of make sure that your math is mathing and that you're getting the understanding that you would expect from your equations, as well as does it fit the evidence or not. So there's a lot of puzzle solving like that. So that's scale factor. And then I wanted to also, because these equations come up over and over, I just wanted to establish them now so that it's not like a mystery. Okay, so we just said what is scale factor, small a, that's scale factor. That's what we're going to use to quantify the fact that the universe is expanding. And then small t is cosmic time. And let me just read the caption for that figure 2 with the boxes there. Expansion of the universe, the co-moving distance between points on a hypothetical grid remains constant as the universe expands. The physical distance is proportional to the co-moving distance times the scale factor. So the physical distance is proportional to the co-moving distance times the scale factor. So it gets larger as time evolves, and the scale factor itself changes as time evolves. Okay? And we even see how the scale factor depends on time. Its dependence on time was different in a radiation-dominated universe than it is in a matter-dominated universe. We actually also did a math earlier in a previous live. I think it was couple nights ago. Sorry, it's like sleep raining right now, so there might be some noises. A couple nights ago, we saw that there is even an epoch of the universe when, like basically, you can figure out the epoch at which the epoch of equality, like when it turned over from radiation dominated to matter dominated, and there's even some math and equal things that you can do to, solve something out then. But we'll get, we already covered that. I just want to go over the basic equations and relationships again. So we've established what is scale factor and what is cosmic time. Now, we will figure out the Hubble rate. To quantify the change in the scale factor and its relation to the energy, it is first useful to define the Hubble rate. So Hubble rate as a function of time is given by capital H or big H of t, and it is defined as the derivative of a with respect to time over a. So I have written that out for your easy digestion right here. So you can see that capital H as a function of time, or the Hubble rate as a function of time, is simply dA dt over a. Okay, so it's not too bad. And this is the measure of how rapidly the scale factor changes. Okay, and from now on, whenever we do any math, we won't do an enormous amount. There will be plenty of words to kind of explain everything, okay? So don't worry about it. The subscript 0 is going to be used to denote the value of any quantity today. So H naught, so capital H of T is Hubble rate, H naught, capital H naught, or with the subscript 0 is going to be the Hubble rate today. Okay? All right. So now, basically now we understand how this is defined. It's just a definition. What is the Hubble rate? Capital H of T, it's simply dA dt over A, okay? So the derivative of the scale factor as a function of, with respect to time, and then all of that divided by A. Now, if you are somebody to whom, if you're new to calculus, so derivative is simply the rate of change of a variable with respect to another variable. So we actually said earlier that the scale factor is a function of time. It's actually a function of cosmic time. In fact, how it depends on time has changed in different epochs of the universe. So because we know that it's a function of time, we know that we can also take a derivative of the scale factor as a function or with respect to time. Sorry about all the, you know. So if you are not familiar with calculus, by the way, so calculus is it's nothing to be afraid of. We're just taking some derivatives, figuring out some change of a certain variable as a function of a different variable. It's very common in physics to take derivatives with respect to time. We have lots of things that are generally functions of time, right? So it's very common to do that. I do have a book recommendation. This is how I taught myself calculus. This is called Teach Yourself Calculus by P. Abbott. Baji, could you please be over here for this particular live? So this is called Teach Yourself Calculus by P. Abbott. And it's a very small book. See how it's a very tiny book. I don't know if you can still buy this or not. As you can see, the pages are yellow from when I was a child and reading that. So, you know, that's just what I would recommend if you need to teach yourself calculus. But right now we're doing very simple stuff. So see, I actually did something for you. So basically, what you can actually plug in for A. So I told you that scale factor A goes as T to the 2/3 in a matter-dominated universe. So when you take the derivative of that, it's kind of like d dt of T to the 2/3. And the way derivative works is you take the 2/3 to the front and you do the T or to the 2/3 minus 1, and you end up with a number. And it basically gives you, I'll just show it to you right here. It gives you that. So you basically have 2/3 T to the minus 1 if you do this dA dt over A, okay? So basically, now that we know the definition of Hubble rate, which is dA dt over A, basically if you plug it in for a matter-dominated universe, you're gonna get the H, the Hubble rate, to be 2/3 T to the minus 1. And hi, Sebastian. I think so. Yes, I've seen you on the live before. Hi. So you can work this out yourself. If you are somebody who's taking calculus right now or have taken it in the past, you can actually work this out yourself by plugging in where there is A. If you plug in T to the 2/3, you will get that. They're good. There's Baji right there. You will get that the H is now the Hubble rate for that particular A is 2/3 T to the minus 1. So sometimes we will be talking about that the scale factor, certain dependence of it as a function of time, and sometimes we might say that the Hubble rate is going as something, you know, as a function of time. It's interchangeable. We know that the Hubble rate is defined as dA dt over A. So if you know A, you can plug it in and get your Hubble rate. So nothing more magical than that is going on. I just wanted to make it very clear. I know, sorry, it was a little boring, probably me talking about the derivatives, but I just wanted to make it abundantly clear that there's nothing too much going on here. There's just the scale factor. It's a function of time. In the radiation-dominated universe, A goes as t to the 1/2. In a matter-dominated universe, A goes as t to the 2/3. Hubble rate is simply dA dt over A. It's a function of time and has A in it as well. It's basically a function of time because A is a function of time as well. So you can take that derivative and you can get some numbers out. So for a matter-dominated universe, Hubble rate is going to be 2/3 t to the -1. Okay? That's a powerful test of this cosmology. So whether this cosmology, as in the model of the universe, is it matter-dominated or not? Well, you can try to figure out, you can try to measure the Hubble rate and see, is it going as t to the -1? Then you would say, okay, yeah, we are in a matter-dominated universe, for example. So H naught and so a powerful test of this cosmology is to measure separately the Hubble rate today, H naught, and the age of the universe today. So you can plug in time and see what its dependency is on time. Here and throughout, subscript 0 denotes the value of a quantity today. In a flat, matter-dominated universe, the product H naught T naught should equal 2/3. Right, because Hubble H is 2/3 t to the -1. So if it's flat and it's matter-dominated, it should just be 2/3. So those are those are where all those dependencies kind of come into as. Hello, how are the kitties? They're good. They're right here. We're doing math. Nice. The Hubble rate is 10 zoomies per day. Yes, exactly. So now that we've established what the Hubble rate is defined as, we will now talk about more generally, the evolution of the scale factor is determined by the Friedmann equation. So we will now introduce, look at this, Baji's over here on my notes, and I'll have to say, excuse me, Baji, I need my notes again. Hi, Baji. I know. He's like, why are we doing so much math? So now that we have the definition of Hubble rate, more generally, the evolution of the scale factor is determined by the Friedmann equation. So now we're going to be introducing a little bit of general relativity, and we will get into the how to derive it and all that stuff later on. But basically, oh, Baji's now, wait, does this show up correct? Maybe it's a little bit, hopefully that shows up correct. But basically, the Hubble, more generally, the evolution of the scale factor is determined by the Friedmann equation. So now, basically, we're saying that the Hubble rate squared is given by 8 pi g over 3 times rho, which is the density of the energy density of the universe, rho as a function of time plus rho critical minus rho naught over a squared of t. So basically, this rho of t is the energy density of the universe as a function of time, with rho naught being the present value, and the critical density is when these things are equal and you just solve for the critical density. So turns out when you do this math, you just get rho critical as 3h naught squared over 8 pi g. So I wanted to show you that because we have talked about the critical density of the universe, and I wanted to tell you exactly where this is coming from here in this math. And big G here is Newton's constant. We will see the, so right now I'm just showing you the equation. We will get to it from a more derivation kind of way and from general relativity in just a little bit here. But basically, this is another important concept to introduce at this time early on. I mean, we've already talked about these in previous live streams, but I just wanted to show you exactly how this math is kind of being developed, because another thing that we have always noted with all of this work is that putting things in terms of the energy density of the universe is very important. We have even seen back over 100 years ago that depending on your value of the energy density, you would actually get a different type of universe. So while you're doing math, you can try different things, right? So we actually saw that depending on the energy density, you could either get a flat or an open or a closed universe. So, over here, while we're defining out scale factor, Hubble rate, cosmic time, we also wanted to show this equation, which is the evolution of the scale factor, which is determined by the Friedmann equation, which really comes from solving Einstein's equation. So ultimately, we will get into Einstein's equations for general relativity in just a little bit here. So keep in mind the critical density is given by 3h naught squared over 8 pi g. This critical density of the universe, exactly what is contributing to this critical density, sort of kind of like thinking about the content of the universe. We actually did the discussion of that already. We actually saw that really in the cosmic inventory there were 5 things. Number 1, photons. Number 2, baryons. Number 3, dark matter. Number 4, neutrinos. And number 5, dark energy. And depending on how each thing contributes to this critical density is how our universe has evolved, or depending on what we see our universe to be doing at this time will tell us something about its energy content, in other words, because we know some things and other things we have to deduce. So we actually saw that when we expected the universe to be, say, matter dominated, as in dark matter dominated, because we also looked at the cosmic inventory discussion earlier, and we saw that dark matter was a lot more than ordinary matter. Out of the 30%, 25% was dark matter. So it's almost like saying dark matter dominated. We actually saw that when you do the math of the universe as a matter dominated universe, you don't get the right result to match with the evidence, and you had to put in dark energy, quite a lot of dark energy. So we actually saw that the dark energy density number had to be something like 70% of this critical density. And we also looked at certain equations of states, certain basically flexibility in how this dark energy might be parameterized for us to get the right results of the universe's actual observation, which is that it was expanding. So things like that. So I wanted to give you sort of where all this initial math is coming from, because we reference it a lot later on. We've already kind of referenced it in the past too, but I didn't go through the basic equations in as much detail. But this is where we get them. Basically, the concept of scale factor is very important in the math, the concept of cosmic time, the fact that the scale factor is a function of the time, the definition of the Hubble rate, which is simply dA dt over A, and then also saying that actually when you put it together with general relativity, the equation becomes h squared of t goes as 8 pi g over 3 times density, which is energy density, also a function of time, plus another term which has to do with the density over a squared. So that equation, once you solve it for critical density, you get this other number 3h naught squared over 8 pi g. So see how so now you basically have a way to solve for the critical density. So you can measure it, because we know 8 is a constant, pi is a constant. We know capital G is Newton's constant, and h naught, if you can somehow measure that, you actually have a number for critical density. So this is kind of how they were able to do all this math and figure out, well, we know the critical density, it's this number. Now let's think about, okay, all the different evolutions of the universe, all the different epochs of the universe, and what was there and what could have been there, and can we figure out how much of this thing was there? Because we saw, for example, they figured out how much matter was there by looking at absorption of light with hydrogen atoms coming from like a quasar, light coming from a quasar, how much of it is absorbed by hydrogen atoms might give you an idea for, they have various ways of measuring how much matter there is in the universe, how much baryonic matter, for example. So those types of things they were able to do, in case you're wondering about how they figured out how much of each type of stuff there is in the universe. Okay, so it's very interesting that you can actually do the math of all this. we will just finish this part just so that we can kind of wrap it up. To use Einstein's equations, we must know the energy density we must know how the energy density evolves with time. This turns out to be a complicated question, because rho, in this rho, the energy density we just looked at, is the sum of several different components. So this is what I was saying. It will be actually several different components actually contribute to it. I just told you what they are, actually the 5 different things we've already talked about in the past, but I'm summarizing it now, each of which scale differently with time. Consider first non-relativistic matter. The energy of one such particle is equal to its rest mass energy, which remains constant with time. The energy density of many of these is therefore equal to the rest mass energy times the number density. When the scale factor was smaller, the densities were necessarily larger. Since number density is inversely proportional to volume, it should be proportional to a to the minus 3. Therefore, the energy density of matter scales as a to the minus 3. So that's one example. The energy density of matter turns out goes as a to the minus 3. But we have actually already talked about cosmic inventory and how each thing in the cosmic inventory, there's only 5 types of things, thank goodness, out of which 3 things we understand mostly. Those are photons, baryonic matter, and neutrinos. These things we understand, and these things we're able to write down equations for. For example, photons we understand are bosons, and so they follow the Bose-Einstein equation, for example. Then baryonic matter, you know, they will follow some other thing. It's not going to be, so let's jump to that part actually so that we can talk about it real quick. So if you later on, not right now, stay in the live right now, but later on, if you're interested, we've covered cosmic inventory. So we saw the cosmic inventory went as, first we had photons, those follow Bose-Einstein, then we had baryons. We got how exactly baryons, they got measurements to see exactly how much of the critical density was being contributed by baryons. We do that. I was gonna say, we also got matter density as a whole by not just looking at the matter density, by looking at matter's interaction with light, which is baryons. Baryons interact with light, but dark matter doesn't. So we also have to look at matter density by getting measurements that are based on gravitational field alone, so that it's not dependent on just on matter's interaction with light. And we also got that. And from that, we got a contribution of 30% of the total matter density, of which only 5% was ordinary matter or baryonic matter. That's how we knew, and some other related things, that's how we knew that dark matter is such a dominant thing in the energy content of the universe. And then next we also saw neutrinos. These, thank goodness, are fermions, so they follow Fermi-Dirac distribution. So we had a way to understand neutrinos in the universe. They're not like, they're very low mass, so it's not like they're going to be a huge thing, but we did do the math for, we did look at the discussion for neutrinos. And then lastly, we looked at dark energy, and it came with this understanding that the universe was expanding. If the universe was matter dominated, then we would have expected certain other, since we can play in these different parameters of the cosmology, like basically if you change the parameters, you get a different cosmology of the universe. You might get a different model of the universe to work. And because it's all mathematics, you can do it. People did it and saw that the one that was really winning was the dark energy dominated one universe, which both had dark energy as well as dark matter, not the one that's like more matter. So we kind of talked about these already in a lot of detail in the few, not the live stream yesterday, but few live streams before yesterday. So the days that kind of followed yesterday. So if you're interested in cosmic inventory and how we did that, we've already covered this. Today we will keep going with the establishing of all our math and equations so that we understand where things are coming from. So we saw scale factor, cosmic time, Hubble rate, critical density, and we also know that critical density is going to be very important in determining the type of universe we get. So it's both important to come up with models that allow for the critical density, to play around with the different numbers. And also it's important to collect evidence that actually give us how much of what thing there is, so that we can put it into the model and see, well, we get this universe, but does that actually then match with the actual evidence that we're collecting on? So that's it's this back and forth of the theory and the experiment, and the theory and the experiment, which together give us the picture of what the actual cosmology and universe currently is. So, but all these equations are incredibly important, so we will establish them. So we know H naught is the current Hubble rate. We know all that. We have kind of covered this as well. Big Bang nucleus synthesis, we covered it when the universe was much hotter and denser, when the temperatures of order MeV, there were no neutral atoms or even bound nuclei. That's when the universe was very radiation dominated. We know that. We talked a little bit about the baryons as well, and how they used deuterium to figure out how much baryonic density was being contributed, and also other ways. There were million other things they did to figure out the baryonic density. It's very important, right, to get that right, because that will also contribute to the rest of the matter density going to dark matter, which is the matter we don't understand. We don't yet know what dark matter is. So all of that, we did that. Okay. We also introduced cosmic microwave background here as well. So moving on now to the smooth expanding universe. So we will kind of see how this next bit flows with all the math being established now. So just as the early navigators of the great oceans required sophisticated tools to help them find their way, we will need modern technology to help us work through the ramifications of an expanding universe. In this chapter, the author introduces two of the necessary tools, general relativity and statistical mechanics. So we will get a little bit of an introduction to these things now, because both of these are important to our understanding of the expansion of the universe. And some of the things we already mentioned, for example, with that Hubble rate equation I gave you, I pulled it out like it's a magic trick, but it actually has a basis, and we will kind of step through that here. So we didn't really talk about how we got this h squared, where this is the big H Hubble rate, h squared as a function of time. How do we get it to be 8 pi g over 3 times rho of t plus some other blah, blah, blah that has to do with rho, where rho of t is the energy density in the universe as a function of time, where rho naught is the present value of it. And we got the critical density also from that. How do we get there, right? So that's going to be general, just a little bit of general relativity we will cover here. Not too much. And we will also cover a little bit of notation. Okay, I know it's not everybody's favorite topic, but it's incredibly important to understand this. So bear with me. Okay, it's going to be really fun. It's going to be great. So ready? Ready, steady. Okay. So we will use general relativity and also statistical mechanics. I don't know how much statistical mechanics we'll do today, but we'll just do a little bit of general relativity today, I think. We will use them to derive some of the basic results that we laid out just now in chapter 1. We talked about these equations I just mentioned. The expansion law, which is really the that Hubble rate equation with the 8 pi g. That comes from general relativity. So we need to kind of understand how it works, right? The dependence of different components of energy density on the scale factor, which governs expansion, the epoch of equality. This is where, so epoch of equality I mentioned earlier briefly, this is the epoch at which the matter density was equal to the radiation density. So really cool. And the luminosity distance needed to understand the implications of the supernova diagram. So luminosity, luminosity distance is something that we have mentioned before. We used it actually to establish dark energy, because when you look at luminosity distances of supernovae data, that's actually how they realize that the universe is expanding. It's incredibly important evidence that tells us, oh my gosh, dark energy is a thing, or there's something that's pushing the universe out and expanding it out. And these luminosity distances are changing of things that should be the same luminosity, but their apparent magnitude of their luminosity changes based on the universe's expansion, not any other thing, but the universe's expansion. So if we don't understand the expansion of the universe and all this stuff, then it would be hard, right? That's why we're going to cover a little bit of math, okay? Implicit in this discussion will be the notion that the universe is smooth. None of the densities vary in space. Yeah. That is incredibly, that is, so note this. When we are, so first of all, we're talking about densities. Densities are basically a mass divided by a volume, right? It's almost like we're not really caring about like the absolute masses, but we're caring about density. And also, so this is another way to, so I always think about the CMB diagram in my head, which is the picture of the cosmic microwave background radiation, which looks incredibly homogeneous everywhere. And that's what people call the smooth universe, for example. But another way to think of it is we're, we're we're saying it's smooth, as in we are not caring about the perturbations around the smooth universe. It's not really, so spoiler alert, it's not going to be totally smooth, right? There's going to be certain anisotropies and certain perturbations around the smoothness. But for now, we will not consider those because those are of a different, they're higher order perturbations. Okay, so we don't care about them right now. And that's another way of saying that the universe is smooth. Wow, yeah. So implicit in all this discussion, all the discussion about energy densities is implicitly suggesting that the universe is smooth and in equilibrium. And we will consider the consequences of this later on in a different next chapter, but right now we're considering the universe to be smooth. So this really is a discussion of the smooth expanding universe. It will allow us to study the smooth expanding universe and basically get the important things going and the sort of zeroth order things going. And then there are higher order perturbations around the smooth universe that we will also get into later on. But this also works because dark energy is such a big part. It's the energy content of the universe is mainly dark energy, right? Which we will establish by the end of this chapter. So pretty much the other things are going to be less important and therefore I imagine able to be described with higher order perturbations, but mainly this is all about the smooth expanding universe, okay? In succeeding chapters, we will see that the deviations from equilibrium and smoothness are the source of much of the richness in the universe. Nonetheless, if only in order to understand the framework in which these deviations occur, a basic knowledge of the zero order universe is a must for any cosmologist. So right now we're doing the zero order cosmology. The most important rough look at the universe, the most important things in the universe look only. We're not going into the nitty-gritty details of the universe, which will come from perturbations to the smooth universe, meaning anisotropies in the smooth universe. It's not really as smooth as, when you look in more detail. So right now, when we set up the math, we are actually gonna set Planck's constant, h bar, equal to c, equal to Boltzmann's constants, equal to 1. So there is a system of units in which you can do that. And we're going to do this, okay? So let me just show you this right here. We're setting h bar equal to c, equal to kb, equal to 1. I know it can be a little crazy, but once you get used to it, you'll see life is better. So most of the cosmology can be learned with only a passing knowledge of general relativity. One must be familiar with the concept of a metric. So now we will consider the concepts of the metric and the geodesic. So general relativity, there is more details to it, but for the purposes of understanding this level of cosmology and that equation I talked about, which is the Hubble rate, and why it goes as 8 pi g over 3 times density, blah, 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 we will kind of get an idea for that here in this math, okay? So one must be familiar with the concept of a metric, understand geodesics, and be able to apply the Einstein equations to the Friedmann, Robertson, Walker metric. thereby relating the parameters in the metric to the density in the universe. So that equation we talked about, the Hubble rate, is the result of applying the Einstein equations to the zeroth order universe. We will derive it in this section. So that's what we're going to do today. So the metric. What is the metric? So before we do that, I wanted to introduce a few other things. So I wanted to introduce that in Einstein's notation, there's a few shorthands that we do. So I also wanted to mention that, are you guys familiar with what is a scalar versus a vector versus a tensor? So most people in their physics and math classes probably get in touch with scalars and vectors. So for example, length is a scalar, but velocity is a vector. So I'm guessing that most people are pretty familiar with scalars and vectors. I'm going to introduce a definition for what is a tensor here right now. It's not going to be too bad, I promise. Because you already kind of know what a tensor is, because you know what a scalar is and a vector is, okay? So I've got the ChatGPT definition of a tensor here for you. A tensor is a generalized math object that represents a multilinear relationship between vectors. So this is very important, multilinear. So general relativity does deal in multiple dimensions. Depending on the type of thing you're doing, it can be, you know, just this 3 spatial dimensions and a time dimension, so just 4 dimensions, or in string theory, people can have like 11 dimensions or more. So this, you know, the dimensions being more is going to be a theme for our math here today. But we're going to, I promise, it's going to be mainly all 4 dimensions, okay, including time. So it's not going to be that bad. We're not doing string theory. We're just doing a very basic general relativity setup today, so that we have that background behind us done, and we can look forward and understand and have the equations ready for a zeroth order universe, or a smooth universe, which is the roughly speaking universe, which is the not considering the perturbations universe, okay? And which gives us, of course, the universe's expansion with dark energy. And because dark energy is most of it, turns out it makes sense that we would capture this effect with the smooth universe, whereas some other things we might need to look deeper to understand better. Okay, again, what is a tensor? A tensor, so this multi-dimension thing, just get ready, okay? A tensor is a generalized math object that represents a multilinear relationship between vectors, essentially acting as a container for data in multiple dimensions, which can be thought of as an array of numbers that describes a physical property requiring multiple directions to fully characterize it. A scalar is a 0-rank tensor. So a scalar is also a tensor, just a 0-rank one, a very simple one, boring one. A vector is a first-rank tensor with higher ranks representing more complex relationships between directions. So think of it as sort of like a container of data, which allows for multi-dimension type things to happen, and linear type of relationships and things to be allowed. It's not like a vector. It's more complicated than a vector, okay? And a vector is a first-rank tensor, and a scalar is a 0th rank tensor. Hi, Olomaro. Hi, Jabo. Hi, Sebastian. Hi, everybody. Hello, hello. So now that we know what a tensor is, we will now talk about what is a metric. Oh no, first we will also, 1 second, bear with me, we're almost there. So we're gonna show you this notation. Can you see? This notation is basically saying that when you have 2 vectors and you want to take a dot product of it, A dot B, basically that's gonna be, so say, you know, A has, you know, if A is a 3-dimensional vector, A has 3 components which we refer to as A superscript I. So A1, A2, A3, for example, you know, like XYZ, but now we're just calling it A1, A2, A3. So we're just giving it superscript I, taking the values of 1, 2, or 3. The dot product of 2 vectors is then A dot B. Summation, going from I equals 1 to 3, of AI, BI, where the i's are in the superscript. So that's what we've written down here. See, we've written down that. In general relativity, it is very common to get rid of that summation sign when you have a repeating index, like I in this case. We just don't write the summation anymore, but we imply that it's there. Basically, if we're saying A dot B is equal to summation going from I equals 1 to 3, AIBI, then that is the same as writing it as AIBI without the summation sign. I'm just letting you know as an FYI that we're going to drop the summation sign in these maths going forward. We're not going to have them, okay? But we are summing over the components of AI and BI, and we know that because of the repeating index. AIBI, the I appearing twice means that there's a summation over I. So it's going to be A1B1 plus A2B2 plus A3B3. So there is a summation implicit by writing down AIBI. Got it? Okay. Next, we will do the same thing, but with product of two matrices, okay? So if you have two matrices, M, capital M and capital N, then Mn, and you take the product of that, for example, the product of two matrices, basically the ijth component is given as Mik and Kj, like this, like that, Mik and Nkj. Again, there is an implicit summation over K here, okay? So this is just going to be a thing. We will drop these summation signs to keep the notation more simple. So we saw it with the vectors. Similarly, matrices can be written in a component notation. So we will be writing down things in a component notation a lot, right? That's why we're getting used to it now. So component notation, again, of the product of two matrices, M and N. Mn in a bracket, ij. So the ijth component of the Mn product is going to be Mik and Kj. Because the K appears twice, we know it's a summation, okay? Implicit summation over K without actually putting in the summation symbol. In relativity, two generalizations must be made. So this is going to be the next part of the math. See, we're almost done. There is just one page of this. We're halfway through. So to understand the math, these types of notations are going to be important to understand. But it's not too bad, especially what we discussed so far. It's very common, okay? Very common. In relativity, in special relativity 2, I think people use that pretty much. So it's not too bad. In relativity, two generalizations must be made. First, in relativity, a vector has a fourth component. So we just talked about the whole AIBI thing. AIBI is really a summation over the components of A and B, A1, B1, A2, B2, A3, B3, and we're summing them, A1, B1 plus A2, B2 plus A3, B3. We're writing them as AIBI, and because we write them as AIBI with the I being in the superscript, we just know this is a sum. We don't have to say it again. I repeated means it's a sum. But actually, another little, mind shift that we need in relativity is that relativity has four components. All these vectors that we will come across will have a fourth component, and this is going to be the time component. And we're going to generally give it the zeroth index. So the zeroth index of a vector is going to be its time index, and the indices that are running from 1 to 3 are going to be its spatial index. Okay, so relativity has in relativity, a vector has a fourth component, the time component. Since the spatial indices run from 1 to 3, it's conventional to use 0 for the time component. Greek letters are used to represent all four components. So A mu is shown like this. A naught or A0 in the superscript, A I in the superscript. What that basically means is that A mu is the vector which has a time component which is in the zeroth index, and AI is pretty much its spatial indices. So nothing special. So far, everything is easy. A mu, where mu is in the superscript, basically just means that it's a general relativity type of vector where mu goes from 0 to 3. That's all. Where 0 is the time component, 1, 2, and 3 are the spatial components, x, y, z, right? Except we don't really write x, y, z generally. We generally go with these mu and I type of notations, okay? The second, more subtle feature of relativity is the distinction between upper and lower indices. So in relativity, you will notice that we've been talking a little bit about dropping the summation sign to simplify the notation. Basically assuming that if an index is repeated, that basically means that you're summing over that index. This is especially useful when you have, say, dot products or something like that, or some product of two things happening where there's going to be a summation needed, and instead of writing it out, you're just using the repeating index to imply the summation. Another little thing, which can be subtle, is that there is a distinction between upper and lower indices. So I showed you a mu. I'll show it to you again, a mu. So this a mu, the mu being an upper index, is not a coincidence. We want to be intentional about our upper and lower indices. So I'll read that part here. The former, so the upper index is associated with vectors, and the latter is associated with one forms. One goes back and forth with the metric tensor. So, apparently they go back and forth. So sometimes the metric tensor, which we'll get into soon here, G mu nu, sometimes they write G mu nu with lower indices, and sometimes they write it with upper indices. Don't ask me why, whatever. A vector and a one form can be contracted to produce an invariant, a scalar. For example, the statement that the form momentum, so momentum is sometimes written as P, capital P, squared of a massless particle must vanish. P squared is P mu. P mu, P mu, the mu's are upper and lower for the two P's. One is a vector, one is a one form. And, once you product that with G mu nu, it goes to 0, whatever. So just keep in mind that there's going to be a difference between upper and lower indices. That also has a meaning. I think we're pretty much ready to look at the metric now. Just as the metric can turn an upper index on a vector into a lower index, basically now is a great time to show you the metric. So the metric, sometimes we call it simply G mu nu, where this G is the small g. Small g subscript mu nu is this thing. It's not a bad thing. It's just a matrix. We call it the metric. I'll tell you why. It just looks like that. Okay, it's just a matrix. See how it's very simple. So it's a matrix. It has 4 diagonal terms. The first one is -1, the -1 for time. The rest are a squared t, a squared t, a squared t, because the metric is very simple. We will see how this converts to, once this is taken together with Einstein's equations, it'll be different. But the metric is simply, this is simply the Friedmann-Robertson-Walker metric. It's just a matrix, and it's got some off-diagonal terms, and the diagonal terms are very simple so far. So far, so good. So that's what we mean by the metric. And this is the metric of this particular type of universe that we'll talk about just now. So let's get into it. So what is a metric? Now that we kind of established some of the notation, I just wanted to go over the notation styles in general relativity so that it doesn't come as a shock. Because really it will take time to get used to it, but just expect that that's how they do the notation. So now we will get into what is the metric. I showed it to you in that matrix form, but really what is it? So, okay, so you might actually be kind of familiar with a different type of metric. So we will start there. So I'm trying to see this part. So we looked at, for example, in chapter 1, where we highlighted the fact that even if one knows the components of a vector, say the difference between two grid points there, the physical distance associated with this vector requires additional information. So we actually saw how the scale factor was needed to figure out what really was the physical distance between 2 points in an expanding universe. In the case of a smooth expanding universe, the scale factor connects the coordinate distance with the physical distance. More generally, the metric turns coordinate distance into physical distance. So this metric will basically allow us to, it's almost like this thing that you product with in order to get the expansion and the form of the universe that you're expecting. That's all. Think of it as like a little container, right? It's like a little data container or a little an object that you have to like product your other thing with. We will get into what the other thing is, and once you do that, you get the right you get the right expansion or the right state of the universe or the right geometry, something like that. So we are familiar with the metric for the Cartesian coordinate system. So we are probably all familiar with the Cartesian coordinate system, right? X, Y, Z, that type of stuff. So we'll start there. And that'll give us a better definition of what the metric is, G mu nu. Hi, Baji. And then once we have done all of this, it'll be behind us, I promise. So let's keep going. So we are familiar with the metric for the Cartesian coordinate system, which says that the square of the physical distance between 2 points separated by dx and dy in a 2D plane is simply dx squared plus dy squared. However, were we to use polar coordinates instead, the square of the physical distance would no longer be the sum of the square of the two coordinate differences. Rather, if the differences dr and d theta are small, the square of the distance between 2 points is dr squared plus r squared d theta squared, which would not be equal to dr squared plus d theta squared. So it's kind of like, yeah, I think you get that, because I think most people understand Cartesian coordinates and polar coordinates. This distance is invariant. An observer using Cartesian coordinates to find it would get the same result as one using polar coordinates. Thus, another way of stating that stating what a metric does is this: it turns observer dependent. Ooh, this is very important. It turns observer dependent coordinates into invariants. That's what it is. Good job, author of this book, Scott Doodleson. So it's basically taking the observer dependent coordinates and turning it into an invariant. So you can imagine that this will be very important in our understanding of how we write down the universe's geometry, or basically understanding the expansion of the universe, or even that Hubble rate term that we wrote down. It'll play into it at some point. So mathematically, in the 2D plane, the invariant distance squared, dl squared, is equal to a summation of I and j going from 1 and 2. So dx, dy, x and y is just two spatial indices, right? Which can be given by I and j, and each one, let's just say, goes from 1 and 2. Like it starts at 1 and ends at 2. Gij, dxi, dxj. So the matrix Gij in this 2D example, this is a 2D example, is a 2 by 2 symmetric matrix. In Cartesian coordinates, the metric is diagonal with each element equal to 1. In polar coordinates, taking x1, so the xi equal to r, and x2, that is the xj, equal to theta, it is also diagonal with g11 equals 1. So everything is being in terms of a matrix here. Okay, so let me actually, so it's literally 2 by 2 matrix, and the diagonal elements are equal to 1. So just like that. It's a very simple one. And I'll also write down G mu nu. And we will see. So we know that x, y is 2D. So we expect a two-dimensional matrix. Since general relativity is going to be 4D, including time as one of the dimensions, you can imagine that it's going to be a four-dimensional matrix. If you have even more dimensions, you would have an even higher dimensional matrix. Okay, so we just saw that when we have a Cartesian coordinate system of just x, y, 2D, we would have a matrix that's just 2D matrix. Now that we are going to be talking about the metric for general relativity, just making sure I got all the zeros and everything. It's going to be four-dimensional. It's going to look like this. I need to get a whiteboard, I know. But yeah, the first term is simply -1 in the diagonal. The rest are a squared as a function of t, and the rest are 0 for this smooth zeroth order type of universe. You could imagine there being off-diagonal terms in a more complicated situation, but we're not starting there. We're starting with this one, okay? So that's what the metric is. And we will keep reading here. There is yet another way of thinking about a metric, using pictures. When handed a vector, we immediately think of a line with an arrow attached. The length of the line corresponding to the length of the vector and the arrow to its direction. In fact, this notion is rooted too firmly in Euclidean space. In actuality, the length of the vector depends on the metric. Right. An intuitive way of understanding this is to consider the contour map in figure 2.1. This map right here looks a little bit like a mountain. It's actually this is a contour map of a mountain is the caption of this. The number of lines crossed by a vector is a measure of the vertical distance traveled by a hiker. Vectors of the same apparent 2D length corresponding to identical coordinate distances can correspond to significantly different physical distances, right? Right, a hiker would know. Mathematically, the surface of the Earth can be parametrized by two coordinates, say theta and phi. Then the metric is a very non-trivial function of theta and phi, which accounts for all the elevation changes on the surface. So this is where you have a bit more detail than just a 2D surface. The great advantage of the metric is that it incorporates gravity. So we will look at this in more detail, but we will see how it incorporates gravity in just a second here. But let's just define out the metric for now. Instead of thinking of gravity as an external force and talking of particles moving in a gravitational field, we can include gravity in the metric and talk of particles moving freely in a distorted or curved space-time. Remember, general relativity is basically a description of gravitation as a curvature of space-time. So this is how it's incorporated into the space-time. It's basically part of the metric. So that's the math we're establishing. That's why, even if a little painful, it's very fruitful to understand where and how this is done at a basic level, because this is a very fundamental to the math of the universe. So we will see in just a second. We haven't really talked about how, but basically we will see that the metric is going to incorporate gravity. In four space-time dimensions, the invariant includes time intervals as well. So the ds squared, the thing that was the dl squared given by dx squared plus dy squared, or, if you wrote it as xij, it would be gij dxi dxj summed over I and j. That same thing here is basically ds squared is equal to the summation going from 0 to 3, because remember we said we would include time as the 0th index, and 1 to 3 is the spatial. G mu nu, dx mu dx nu. Okay, so the way to write that down is right here, and later on we won't write the summation symbol anymore. As soon as you see a repeating index, you will know. Hi, Fuji Bablu. Hi, baby. Are you okay? Are you learning? Good job, Fuji. You're so soft. Okay, babe. You will know that it's summed over. Okay. So this is what we're talking about now. This is going to be the invariant in 4 space-time. ds squared is a summation over mu and nu going from 0 to 3. G mu nu, that's the metric, we'll use dx mu dx nu. Okay, just like in 2 dimensions, but now in 4 dimensions. Okay, and so the metric will also be 4 dimensions, where the indices mu and nu range from 0 to 3, with the first one reserved for the time-like coordinate. So dx0 is basically dt, and the last 3 for spatial coordinates. I've explicitly written down the summation sign here, but from now on we will drop it, because whenever we have repeating indices, it basically means you're summing it over those indices that are repeated. The metric g mu nu is necessarily symmetric, so in principle has 4 diagonal and 6 off diagonal components. We looked at it actually. It provides the connection between values of the coordinates and the more physical measure of the interval interval ds squared, sometimes called proper time. Special relativity is described by Minkowski space-time with the metric g mu nu is equal to eta mu nu with. So special relativity is more simple, right? Thank God. So it's just like g mu nu, except the diagonals are literally -1, 1, 1, and 1, and the off diagonals are all zeros. So now our life is not as simple, but not too difficult either. For general relativity, what is the metric? Or sorry, we are not actually into general relativity too much yet. We simply want to write down what is the metric describing the expanding universe, then we'll come to how. So we said earlier that 2 grid points move away from each other so that the distance between the 2 points is always proportional to the scale factor. So we introduced, remember, the concept of the scale factor given by small a earlier on in the beginning of the live. And in pretty much all our lives, we talk about the scale factor. It's very important. It's that same thing that is a function of time, and how it depends on time is given by the type of universe, the matter, the radiation-dominated universe, a scale factor a went as t to the 1/2. In the matter-dominated universe, it goes as t to the 2/3. So it's a function of time. So now we're trying to come up with a metric which can describe the expanding universe and also give us a connection between our coordinate system for the 4 space-time as well as the expanding universe, right? So we know it's going to concern small a probably. If the co-moving distance today is x0, x naught, let's call it x naught. The 0 is now a subscript, because remember, if it's a superscript, then it means it means that it's an vector index. The physical distance between the 2 points at some earlier time t was a of t x naught, at least, right? At least in a flat as opposed to open or closed universe. The metric then is almost identical to the Minkowski matrix, where the Minkowski matrix is simply the matrix which has pretty much 0 non-diagonal terms, and just -1 is in the, I'll just write it down real quick. The Minkowski metric is very simple. It looks like this. I really, really need a whiteboard. It looks like that. That's the Minkowski matrix. So it's going to be very much like that, but a little different. So we actually already know it's going to be like that, except for the space ones, the spatial, because the universe expands and we know that the scale factor is involved, we describe it with scale factor, the expansion of the universe. That's why the metric, the Friedmann, we call this the FRW metric or the Friedmann-Robertson metric for an expanding flat universe. So remember, it's going to be a little different for closed and open universes. We're not going into those models right now. Just for the expanding flat universe, it'll be this one. So a lot like the Minkowski metric, but with a squareds in the corresponding to the spatial diagonal terms. So as noted, we will now derive the Hubble rate equation. So now that you know that we in general relativity, we have four space-time dimensions. Time is the first one, the 0th one, space, it goes from 1 to 3. You also know about the metric. You also know about Minkowski metric. So you kind of know the metric in special theory of relativity versus general theory of relativity. You kind of know some of the notation styles we're using. Now we will get into the geodesic equation. Okay, so we will also cover that briefly. We won't necessarily look at all of the math. We will cover it briefly. So, how's everybody doing? So in Minkowski space, particles travel in straight lines unless they're acted on by a force. Not surprisingly, the paths of particles in more general space-time are more complicated. The notion of a straight line gets generalized to a geodesic. So basically a geodesic is gonna be sort of a straight line, but like in general relativity. The general relativity equivalent of a straight line is going to be a geodesic. So it's not too bad. It's not too complicated of a concept. So the notion of a straight line gets generalized to a geodesic, the path followed by a particle in the absence of any forces. Yay! To express this in equations, we must generalize Newton's law with no forces. So d2x dt2 equal to 0. So remember how the whole F equals ma. The a is acceleration, right? So it's really the second derivative of position with respect to time, right? And basically what it's saying is that your second derivative of your position with respect to time, that's going to give you acceleration, and acceleration is caused by a force, right? So if you're saying that there's no force, then you should not be accelerating, and so your second derivative should be 0, right? So d2x dt2, and by the way, x is a vector here, because why not? So simply your second derivative of position with respect to time, if you're not acted on by a force, is going to be 0. Like this. d2x dt2, 0. So to express, we must generalize Newton's law with no forces to the expanding universe. The machinery necessary to, because he described, so Einstein described gravitation as a curvature of space-time, right? So that means that there is no force until, of course, later on. So until we have to do other things. But for the time being, if you're only considering gravitation as the force, and it's not really a force in general relativity, then your d2x dt2 is a 0. How cool is that? Okay, so after doing that, he just pretty much has to write it as, so first d2x dt2 particle motion in a Euclidean 2D plane. They write that down. In that case, the equations of motion in Cartesian coordinates would simply be d2xi dt2 is equal to 0. In polar coordinates, it would be x prime. So whenever, if we change coordinate systems, we add a prime, usually x prime I equals to r theta now. Instead, the equations for a free particle look significantly different. So it's kind of like we're writing down the equation for a free particle, meaning that when there is a free particle in this universe, and the only thing we're considering right now is gravitation, and gravitation is part of the fabric of space-time, basically you can just say that this free particle doesn't really have an acceleration. It's d2x I dt2 is equal to 0, which is amazing. So then there's more math. Fuji. No. I'm just trying to see how I can summarize this without going through it too much. Fuji. No, Fuji. Hi, Fuji. Okay. So they go from the polar coordinates to the Cartesian coordinates, and that gives us certain more equations, but literally we started just with d2x I dt2 equal to 0. So that's progressing more and more. And then, oh, I see. Here, 1 second. Give me 1 second. We will, oh my gosh, Fuji, you're getting caught up in the wiring. No. I'm trying to see how to summarize the geodesic for you in the best possible way. But I think it's already insightful to think of this as simply d2x dt2 is equal to 0. This is already helpful. I'm just trying to give you a summarized version of where we end up when we do that. There's a lot of math here. I'll show you. There's like a few pages of math now, which is a little bit hard to summarize, but let me try. There is a Christoffel symbol thing that we have to talk about. That's okay. That's okay. Oh, yes. Okay. So they went from the Cartesian coordinates to polar coordinates. I wasn't, they didn't really say why, but whatever. It's convenient to define the Christoffel symbol. This is going to be important too. There is this symbol called Christoffel symbol, which has, it looks like this. Let me write it down. That will also come back. Where are we? Yes. It's like this JK. It looks like this. The third thing here. Kind of like an L, but the other way around. And then the superscript is L and the subscripts are J and K. To be the coefficient, note that the definition is symmetric in its, by definition it is symmetric in its lower indices J and K. In a Cartesian coordinate system, the Christoffel symbol vanishes and the geodesic equation is simply d2x I dt2 equal to 0, but in general, the Christoffel symbol does not vanish. Its presence describes geodesics in non-trivial coordinate systems. The reason why this generalized geodesic equation is so powerful, so they're going to be using a more generalized geodesic, not just a Cartesian system kind of geodesic, because there's four spatial dimensions, or 4 space-time dimensions. There are 2 small changes we need to make when importing the geodesic equation into relativity. The first is trivial. Allow the indices to range from 0 to 3 to include time on the 3 spatial dimensions. The second is also not surprising since time is now one of our coordinates. It will not do to use it as the evolution parameter. Instead, introduce a parameter lambda, which will, this is small lambda, which will monotonically increases along the particle's path, as in figure 2.2. So it looks like this. So you can't, time is one of the dimensions, so we have to have a new little symbol called small lambda, which will tell us that that's increasing along the particle's path in space-time. The geodesic equation then becomes d2x mu d lambda 2. So basically it's going to end up like something like this. It started with d2x, dt2 is the beginning part of it. That's how we understand normally. But in general relativity, after doing some of this special accommodations for having 4 space-time, we get the following. D lambda squared is equal to, this Christoffel symbol will be important now. Fuji. Look. Don't do that. Okay. Okay. I'm just looking to make sure. dx alpha. Ooh. Right. D lambda. There's going to be 2 derivatives. Ooh. We will figure those out too. So it's going to be alpha and beta. What are alpha and beta? It is will you tell us what is alpha and beta? Ooh, the derivative is non-zero. So alpha and beta are spatial indices. So basically, oh, I know. Okay, I see. Okay, so it's gonna look like this: d2x mu d lambda squared is equal to the Christoffel symbol dx alpha d lambda dx beta d lambda. Lambda is that sort of, you know, the variable we have to use because we can't really use time, because time is part of the space-time now, part of the fabric of, you know, space-time. It's one of the things that also will be changing. So we derive this equation transforming from a Cartesian basis. So they're basically going from Cartesian to this other form so that they can accommodate that this is not a Cartesian coordinate system anymore. This is a new coordinate system which has 4 space-time. The time is the 0th index. The others are the spatial indices. And also you need this other parameter lambda, which monotonically increases along the particle's path. And then what does d2x, dt2 look like? That's what it looks like. That thing right there. So after doing more things to figure out the rewrite it again and again and again, the first using the general expression and the FR. So now they also can write down, we derived this equation transforming from a Cartesian basis so that the Christoffel symbol is given by the term in square brackets. It is almost always more convenient, however, to obtain the Christoffel symbol from the metric directly. So now the Christoffel symbol is actually introduced or written down in terms of the metric. So actually, let me just show it to you like this. So we needed the Christoffel symbol in the first place because it's not just one in this particular type of coordinate system. It's actually got to do with that metric thing, right? So again, now note that the raised indices on G mu nu are important because G mu nu with the raised mu nu is the inverse of G mu nu with the subscript. So G mu nu raised in the flat FRW metric is identical to G mu nu subscript, except that its spatial elements are 1 over a squared instead of a squared. Okay. Using the general expressions now, we can derive the Christoffel symbol in an expanding homogeneous universe. First, we compute the components with upper index equal to 0. Since the metric is diagonal, it just has the diagonal elements, the factor of G 0 nu. So because now we have G mu nu, now imagine, hi Kayla. Hey, missed you all. Thank you. I'm dressed and ready for school, but my tummy hurts so bad. I got my pills, but I have to take them in class. Wow, you have school. Hi, evil green dog. Have you found us in the middle of the metric and geodesic discussion? Thank you for saying hi, Kayla. Hope your tummy feels better. It's school time in the UK. So now we just want to wrap this up. This has been so even the author is saying this has been a long, rather formal, thank you so much, yes, subsection opening with the generalization of the geodesic equation to curved space-time. So first things first, this geodesic is not the straight line in general relativity is a geodesic. Also, in general relativity, gravitation is part of the space-time, of curvature of space-time. Oh, thank you. Love your outfit. Thank you so much. Yes, I like it too. Thank you. Thank you, thank you, thank you. So because gravitation is part of space-time, basically that is to say that the force on a free particle in the universe is 0, which means d2x dt2, the second derivative of position with respect to time is 0, which when written in this weird space-time coordinate system is going to look a little different, and we will need that metric we introduced. All that done now. Basically, we come to this point where, so we open with the generalization of the geodesic equation to curve space-time and then proceeding with the calculation of the Christoffel symbol in the expanding universe described by the FRW metric, which is that G mu nu. Before completing our main task and using the Einstein equations to derive the Hubble rate, which is what we're after, let's take a break and apply the geodesic equation to a single particle. In particular, let's see how a particle's energy changes as the universe expands. We'll do the calculation. Fuji. Where is Fuji? I thought there was a noise. We use this 4-vector. We'll do the calculation here for a massless particle. An almost identical problem for a massive particle is relegated to exercise 4. Start with the 4-dimensional energy momentum vector, P alpha, whose time component is the energy. So this is just an example. I think it's fine, the 0th component. It kind of takes us through, if you're interested in this book by Scott Dodelson, Modern Cosmology, page 31, there is a sort of simpler example of how to use this type of geodesic and metric to get the particles energy changes as the universe expands. And because there is mass energy equivalence and space-time is like basically the same sort of thing that we did with space-time, where time was the 0th index, you can do that with energy momentum vectors as well, where the 0th, the time component is basically energy, and the others are momentum. So there is an example which is simpler here for that. Hi, Mia. Hello. So we won't waste time with this. This is just an example. We'll get into Einstein's equations now. So hopefully we are kind of seeing that the math is going to be a little different here, only because we're not in Cartesian coordinates. Sorry, my computer is acting strange. What topic are we discussing, if you don't mind? So we are establishing the basic equations for the expansion of the universe and the sort of general relativity that we need to do that. We're just establishing certain basic equations so that we kind of discuss them now, and then we can just take them for granted going forward. So it's been a session of just defining out some things. We defined out the scale factor, cosmic time small t. We introduced something called the Hubble rate, which basically gives us the expansion of the universe. We did not really say how we got it, but we sort of talked about how it depends on energy density and scale factor A. And then we looked at the fact that general relativity and the universe is not described by Cartesian coordinates. General relativity has four dimensions with space-time. The time dimension is denoted by the zeroth index, and the spatial dimensions are given by index 1, 2, and 3. We also looked at how certain notations used in general relativity when you're summing over things and there's a repeating index. You just assume it's summed over. You don't put the summation sign anymore. We also saw that just like in Cartesian coordinates, there are certain invariants. The same thing here would be the metric, what we've been calling the metric. And that metric will be different for different models of the universe, but for the flat expanding universe, it's given by the FRW metric. We saw what that is. It's just a matrix that's four-dimensional in this case, and there's terms in the diagonal. And that's it for this simple case. We also saw the concept of a geodesic, which is basically sort of the path a free particle in the universe would follow if no forces were acting on it, sort of like a straight line. You know how in Newtonian mechanics we had the straight line, like a particle would just follow a straight line if nothing was accelerating it. The same thing sort of is true here, except here we're not considering gravitation as a force, we're considering as part of the fabric of space-time. So a free particle under gravitation is actually not under any force, so we can write down the second derivative of its position with respect to time as 0. But there is a complication because this is not a Cartesian coordinate system. The coordinate system of general relativity with this four space-time is a little different. So we've been establishing how it's different and kind of how that gets written down, and we got some taste of it, let's just say. And now we're ready to move forward and get into Einstein's equations, because so far everything was to do with establishing the math. I see. Thank you. Let me get my neurons flowing to this. Haha. Yes, it's a great time to make new neuron connections in this live stream. So Einstein's equations now. If you did a word search on the previous two subsections, you might be surprised to discover that the words general relativity never appeared. As we were discussing metric and geodesic, that's sort of, it's non-trivial math, but it is not necessarily only about general relativity. That's what the point of this is. So the concept of a metric and the realization that non-trivial metrics affect geodesics both exist completely independently of general relativity. It's sort of a math thing. So general relativity is sort of a math thing, right? A lot of mathematicians might be more comfortable with it than us physicists, but here we are. The part of general relativity that is hidden above in what we just talked about is that gravitation can be described by a metric. So this is where I was getting excited earlier, but the author wasn't really illuminating it at that time. But remember how I said that the only reason we can write down d2x, dt2 equal to 0 in this context is because gravitation is not a force anymore, and general relativity is part of the fabric of space-time. And so that's why, because in Newtonian mechanics, remember the whole entire thing, like the F equals ma And really F equals mg when the acceleration is under gravity, the g, the small g and the small a are the same thing there in Newtonian mechanics. That's all considering gravity as a force. So this is a big leap. The big leap here is that gravity is part of the metric. Gravity is not a force. It's almost like Einstein took a bunch of complicated math for geodesics and metrics that give you this way of writing things down. That's like for a different coordinate system that we're not generally used to, because we generally usually just do Cartesian coordinates or polar coordinates or something like that. And then he put gravity in the metric. You know, the part of general relativity that is hidden above in what we just discussed is that gravitation can be described by a metric. In our case, by equation 2.4, which is what we looked at earlier. This is that equation. I showed it to you, this equation. So see how g mu nu is the metric, right? It's basically a matrix which has diagonal terms of -1, a squared, and a squared. So let's see. There is a second aspect of general relativity, though, one which relates the metric to the matter and energy in the universe. This second part is contained in the Einstein equations, which relate the components of the Einstein tensor, describing the geometry of the energy momentum tensor, describing the energy. So now there's going to be another tensor. So now big G mu nu is going to be Einstein tensor. So this is why I defined what a tensor was earlier. So real quick, a tensor is a container which will... Let me read this again. A tensor is a generalized math object that represents a multilinear relationship between vectors, essentially acting as a container for data in multiple dimensions, which can be thought of as an array of numbers that describes a physical property requiring multiple directions to fully characterize it. A scalar is a 0th order tensor and a vector is a 1st order tensor. Okay, so capital G mu nu is going to be the Einstein tensor. Capital R mu nu is going to be the Ricci tensor, which depends on the metric and its derivatives. So the Ricci tensor, and there's going to be a curly R, which is going to be the Ricci scalar is the contraction of the Ricci tensor. So remember how we talked about Ricci? Hello, looking flawless on this beautiful night. Oh, thank you, Crazy Eddie. Hi. I'm an MIT dropout, wanted to become a theoretical physicist, but had no discipline. You can still come back to MIT. Or not. I'm an MIT dropout too. As in I worked there and no longer work there, so. But I did not go to school there. So I've heard it's hard. And costs a lot of money. So maybe that's a good idea to be dropout. It costs too many thousands per year. I like it when MIT pays me instead. So, yes. Okay. So Ricci tensor, which depends on the metric and its derivatives. So we know what the metric is. It's G mu nu. We saw it. It's a matrix with that -1 and the a squareds in the diagonal and zeros everywhere else. Capital G is Newton's constant. T mu nu, there's going to be a capital T mu nu. That's going to be the energy momentum tensor. We will spend some time on the energy momentum tensor here for now, or in a bit. For now, we need to know, all we need to know is that it's symmetric tensor describing the constituents of the universe. So it's a symmetric tensor. Definitely, yes. Thank you for coming to the live, Crazy Eddie. So all we need to know for now about the T mu nu is that it's an energy tensor, energy momentum tensor, which is gonna describe the constituents of the universe. We did spend some time on cosmic inventory already, which is actually the later part of this chapter. So we kind of looked at that already. We're establishing the math now in this live stream, but you might know about that already. The left-hand side of the equation here, which is a function of the metric. So this basically says r mu nu minus 1/2 small g mu nu curly r is 8 pi g. So see how some of those 8s and pi's and g's are now coming back? I'm 28, so I better think of something fast. What do you mean? "28 is a very young age. Is that what you mean?" You have all the time in the world to become a theoretical physicist if you wish. Correct, live, if you are gonna do it. We are becoming a little theoretical today. So, left-hand side. So here we will have the Einstein tensor. It's gonna be, I apologize on behalf of cosmologists for using some of the same variables for everything. Here, capital G mu nu is the Einstein tensor. It's not Newton's gravitation constant. Capital R mu nu is, of course, the Ricci tensor. And then the same R written in a curly way is the Ricci scalar. Yay! And then small g mu nu is the metric. We've already met the metric, thank God, so we don't have to spend more time too much doing that. And then capital T mu nu is the energy momentum tensor. So there's a bunch of tensors here, which is fine because it's not one-dimensional or two-dimensional math anymore. We're talking about the universe and 4 space-time dimensions. Time is the 0th dimension. Space is dimensions 1, 2, 3. So these things go from 0 to 3. So the indices are going to be 0, 1, 2, and 3. Whenever it is a mu or a nu. So that's that. Now, we know that this r mu nu minus 1/2 g mu nu curly r is obviously related to the metric. So some math later, what do we get? It would be great, Scott Doodleson, if you just told us how... Sorry, one second. My foot is stuck. Oh my God. Okay, all right. Okay, one second, please. So, I just want to know where the 8 pi g comes from. Thank you very much. In a succinct manner, so I can tell my audience in a succinct manner. So, oh yeah, that's right. So they're taking some derivatives now of the scale factor. So there are some a dots and a dot dots. So let's just read this part. The Ricci tensor is most conveniently expressed in terms of the Christoffel symbol. That other thing we talked about earlier with that weird this way thing, alpha mu nu. The commas, oh yeah, there's another thing. Commas denote derivatives in general relativity notation. Because we don't want to keep writing down derivatives because we take derivatives all the time, sometimes we have a comma. And that comma means that there is a derivative with respect to x. So, is that lambda? No, gamma, that's gamma. The Christoffel symbol is given by gamma, right? This thing is gamma, right? This thing. Gamma alpha mu nu comma alpha means that there is a derivative of gamma alpha mu nu with respect to x alpha. So let me just show you the Christoffel symbol again. See, that's the Christoffel symbol right there. This one, I think it's a big gamma is the name of that symbol. Correct me if I'm wrong. Although this expression looks formidable, we have already done the hard work by computing the Christoffel symbol. So we already looked at that in the FRW universe. It was kind of painful, but whatever. It turns out that there are only two sets of non-vanishing components of the Ricci tensor, one with mu equals nu equals 0, and the other with mu equals nu equals I. Consider R00. So I remember now, this was a painful process in my GR class where we then wrote down like R00 and R this. Like basically you can write down these components of the Ricci tensor, and it basically is like R00 is equal to gamma alpha 00 comma alpha minus gamma alpha 0 alpha comma 0 plus gamma alpha beta alpha. You know, there is a lot of Christoffel symbols in that equation now. Recall that the Christoffel symbol vanishes if its two lower indices are 0. So the first and third terms on the right vanish. Similarly, the indices alpha and beta in the second and fourth terms must be spatial. So we're left with just writing down R00 is minus gamma I 0I comma 0 minus gamma I J0 gamma J 0I. So now that boils down to, because thank goodness, this Christoffel symbol, which I'm really not a fan of, is really connected with the metric, which was, remember, a matrix of 4 dimensions, which just had diagonal terms, namely -1, a squared of t, and a squared of t. Thank goodness in this FR freaking W universe. R00 is simply -3 times a dot dot over a minus a dot squared over a squared. That there's a bunch of a's, obviously, because the metric has a squareds, and then another term, whatever, -3 something, whatever. The factors of 3 on the second line arise since delta II means sum over all 3 spatial indices, whatever. Counting 1 for each, I will leave the space component. Oh my God, whatever. The next ingredient is the Einstein equations, is the Ricci scalar. So we must talk about the Ricci scalar now, which can now compute. Since, so the curly R, Ricci scalar is G mu nu R mu nu, which is minus R00 plus 1 over a squared RII, which is the spatial. A physicist's mind has always intrigued me. Brilliant. Do you think physics or mathematics at its top level is more challenging? Of course it's mathematics, because it sucks. Physics is way better. Again, the sum over I leads to a factor of 3. I will gladly say that mathematicians are more clever. I don't care. So the Ricci scalar is 6. Somehow now there's a fucking 6. Because there is, because we took a derivative of a dot dot, or sorry, a dot squared. So that 2 came down. Okay. Okay, so now the Ricci scalar is 6 times a dot dot over a plus a dot over a squared. Okay, to understand the evolution of the scale factor in a homogeneous equation, we need consider only the time component of the Einstein equations. Wow. Oh, thank you. Why? You didn't say why. Oh! Wait. Would you understand that? Oh, wait, what? Why not the other ones? So, you know, remember how the metric is -1 and then a squared. The time component is just -1. It doesn't even depend on the time component of the metric is just -1. So why is it R00? R00, R, so okay. R00 is just the time, right? Got it. Time component of the Ricci tensor. To understand the evolution of the scale factor in a homogeneous, why are you saying that? We need consider only the time component of the Einstein equations. R00 is R time minus 1/2 G00 G mu nu. That's G time. Ricci scalar is equal to 8 pi G. I'm not sure what that means actually. I don't know why you only need the time. There's definitely the other. Oh, are you saying that the other diagonal terms are? I would think that you need all the diagonal terms. What do you guys think? 8 pi G. I thought we would get to the bottom of this 8 pi fucking G, but we don't. I remember doing this though. I thought we would in this chapter. I'll figure it out and tell you later if I can't figure it out tonight. That's crazy. One second. The terms on the left sum to 3a dot squared over a squared. Okay. And the time component of the energy. Oh, so the 8 pi G is not something we've derived yet. So remember that there is an energy momentum tensor in this equation. The big G mu nu, Einstein's tensor is equal to Ricci tensor minus 1/2 metric times Ricci scalar is equal to 8 pi G times T mu nu. So this, I think they just haven't told us yet. The time component of the, so they haven't shown us what the energy momentum tensor is yet. And he's doing the math simply of the left-hand side. We actually, so, I'm stupid. So this is just him writing down the math of the left-hand side. We haven't, I thought we were supposed to get the 8 pi G here, but we're not. So this is simply, basically, he's taking the left-hand side of this. See how there is the Ricci tensor minus 1/2 G mu nu, and then Ricci scalar. Currently, we're just looking at the left-hand side of that. And we're saying that if you just put time here, R00 minus 1/2 G0, R00 minus 1/2 G00 Ricci scalar is equal to 8 pi G T nu, T00. So that's only because, so he said that we need the time, that's because we're looking at the time component. That's it. There's no other bullshit here. Okay. The terms on the left sum to 3a dot squared over a squared, and the time component of the energy momentum tensor is simply the energy density rho. So we finally have this. So basically, we haven't looked at the energy momentum tensor yet, but we just know that the time component of it is just rho, energy density of the universe. And we know that the left-hand side, which is the Ricci tensor's time minus 1/2 G00. And remember G00, G time is just minus 1. And Ricci scalar, we found through some pain here, is 6 times some other stuff. So there's some A dots and things like that. So it turns out to be this. That's where we're at. We still don't know about the 8 pi G yet, okay? We're simply we were writing down the left-hand side so far. So it's all good. Okay, to get this into the form of the Hubble rate equation that we talked about earlier, Recall that the left-hand side here is the square of the Hubble rate. So yeah, we wrote down that the Hubble rate is, of course, dA dt over A. So when you have these A dots, and A is just, you know, if you put in Hubble rate instead, you will get h squared over t, or h squared of t over h naught squared is rho over rho critical. So basically this is to say that that we get that same Hubble rate equation that we started with in the live. We can get this through putting together Einstein's equations with the metric and everything like that. And Einstein's equation is really Einstein's tensor is actually equal to Ricci tensor minus 1/2 of the metric Ricci curly Ricci scalar, which is 8 pi g times the energy momentum tensor. And we don't know, we have not been told about the energy momentum tensor too much yet, except for that its time component is energy density, rho. So here the energy density rho counts the energy density from all species. So this is not just the energy density, meaning, you know, radiation. It's actually the energy density from all the species or all the ingredients of the universe, which is matter, radiation, and dark energy. And more specifically, we saw its photons, baryonic matter, neutrinos, dark matter, and dark energy. 5 things in our universe only. That's already, we did that already without all this math. We said that there were only 5 ingredients in the universe: photons, baryons, non-baryonic dark matter, neutrinos, and dark energy. So when we write down the energy momentum tensor and we write down rho as the energy density, which is the time no, I'm not sick, I'm fine, which is the time component of the energy density, momentum tensor. Good to see you, genius. Are you a little sick? We still love you. Thank you, Peter. Thank you so much for your support. I don't think I'm sick. I hope not. You know, it's just like a little dry, you know, because of the winter time, and my sinuses are a little bit whatever. But yeah, no, I'm good, I think. But basically, this energy density rho counts the energy density from all species, matter, radiation, and dark energy. In our derivation, we have assumed that the universe is flat. So far, all of that stuff we did with the, especially with the metric, remember the small g mu nu metric is written for an FRW, flat expanding universe. So we don't contain a term. So all of this does not contain a term corresponding to the curvature of the universe. Like if you were going to show this for a flat universe or a closed universe, the math would be different, okay? But you could still do that. Good to see you. Thank you, Peter. How are you? How are you doing? So basically, if you were to do all this for the closed version of the universe or the open version of the universe, you would have the math be a little different. We have done it for the flat universe, which affects how we write down our small g mu nu or the metric. So, so far so good. We have discussed that the general relativity math is kind of different. It's not Cartesian coordinates. It's 4 space-time coordinate system. We don't have straight lines when you have a free particle, as in following a straight line. We have geodesics. So we've introduced the concept of the metric, which is the invariant of such a thing, of such a coordinate system. And then we also have introduced the concept of a geodesic, which is what a free particle would follow in such a system of coordinates. We also have some math of what this metric looks like for a flat expanding universe, and it has a lot of dependence, of course, on the scale factor that we introduced earlier. And then time to learn some more. Oh, good! Yay! And then we also saw how Einstein's equations are related to the energy momentum tensor. Oh, actually, some people just do this. You know, the Ricci tensor, when you first start GR, people just do this. Basically, Einstein's tensor is simply 8 pi g times t mu nu, where t mu nu is going to be a very important tensor because that's going to be our energy momentum tensor that we haven't really talked about yet. We just know its time component is rho. But that's where we will probably meet the energy density of the universe and things like that. And then basically we needed to understand the how Einstein's tensor relates to the Ricci tensor and Ricci scalar so that we can get this other math. So the Ricci curvature math helps us to put everything in terms of the scale factor. That's what it is. Basically, that whole Hubble rate equation that we got earlier, it had the scale factor, right? All of that kind of comes from the Ricci tensor math. And then to put it in terms of the energy density comes from Einstein's equation. Einstein's tensor puts everything in terms of the 8 pi g times the energy momentum tensor. So when you bring it together, when you realize that the Einstein tensor is sort of a form of the Ricci tensor and some other shenanigans, and then also his right-hand side is the 8 pi g times the energy momentum tensor, then you can get a relationship between the scale factor of the universe, which tells us about its expansion, and the energy density of the universe. So that's where all of it comes together. But we still don't know. It's important to know what we don't know, which is that we haven't actually defined out the energy momentum tensor yet. All we know is that probably it has some energy densities in it. So now what does this guy do? Oh, good. Here is the energy momentum tensor. I'm gonna kinda ignore the next 2 pages, which talks about the co-moving distances and all that. I don't care right now. Let us return to the energy momentum tensor on the right-hand side of the Einstein equation. So remember, Einstein equation, most people, so right here, we looked at it in terms of the Ricci tensor, but that's not how people might introduce you to it. People might just do the simple version of it, which is the G mu nu, where capital G mu nu is the Einstein tensor, is equal to 8 pi g, where this G is the Newton's gravitation constant G, times the energy momentum tensor, or the T mu nu. And this T mu nu is right here. We will look at it. So this T mu nu that's in the right-hand side of Einstein's equation, we will eventually, so this is going to be very important. So let's think about this. So right now, we are simply talking about a simple, smooth, expanding universe. Remember, we're not worried about higher order type of perturbations to the smooth universe, which might give us other effects. We will eventually include perturbations to this T mu nu, but in the spirit of this current time of this discussion, we will consider a perfect isotropic fluid. So then T mu nu is basically also a tensor with only diagonal terms. And the first diagonal term is simply negative rho. It looks a lot like that G mu nu, the metric matrix. And then the other diagonal terms are given by a big P, where big P is the pressure of the fluid. So all these tensors, for the smooth universe at least, look kind of similar. So you could imagine when it's kind of like saying that for now, we don't care about the non-diagonal terms. So my P's are not as fancy as the P's that they want here. Oh, whoops, I did that. did that wrong. So the first diagonal term of T mu nu is minus rho. It's not P. The other ones, the spatial ones, are P, okay? So the energy momentum tensor looks like that for a smooth universe. It basically, we don't care about the non-diagonal terms right now. We don't care about perturbations. In other words, perturbations to T mu nu or perturbations to the smooth universe. We care about this smooth universe. So what is this P? It's pressure of the fluid. And that first term in the diagonal, the first diagonal term is minus rho, where rho is the energy density of the universe. And this energy density consists of all the different components of the universe's energy, all of the cosmic inventory stuff. Photons, baryons, dark matter, dark energy, neutrinos, everything. Okay? It's not just about an energy as in photon or anything like that. Everything is part of that energy density. So how do the components of the energy momentum tensor 322, how do the components of the energy momentum tensor evolve with time? Consider first the case where there's no gravity and velocities are negligible. The pressure and energy density in that case evolve according to the continuity equation, which is partial rho partial T is equal to 0, and the Euler equation, which is partial P partial xi is equal to 0. This can be promoted to a 4-component conservation equation for the energy momentum tensor, which is partial T mu nu partial x mu is equal to 0. In an expanding universe, however, the conservation criterion must be modified. That's right. Instead, conservation implies the vanishing of the covariant derivative. So again, we will write down things in terms of the Christoffel symbol. And some things will happen. We won't get into it right now, because it's going to be really hard without a whiteboard. The conservation law can be applied immediately to glean information about the scaling of both matter and radiation with the expansion. Matter has effectively 0 pressure. So, okay. So now we're getting into these rho m's and stuff like that. Like, it's not just rho. We will have rho subscript m. Apparently that goes as a to the minus 3. We anticipated this result earlier based on the simple notion that the mass remains constant while the number density scales as the inverse volume. So turns out energy density of radiation, the rho r is going to go as a minus 4, accounting for the decrease in energy per particle. Decrease in energy per particle as the universe expands. Through most of the early universe, reactions proceeded rapidly enough to keep particles in equilibrium, different species sharing a common temperature. We will often want to express the energy density and pressure in terms of this temperature. For this reason and many others which will emerge over the next few chapters, it is convenient to introduce the occupation number or distribution function of a species. This counts the number of particles in a given region in phase space around position x and momentum p. The energy of a species is then obtained by summing the energy over all phase space elements. Fine. How many phase space elements are there in the region of volume d3x, d3p? By Heisenberg's principle, no particle can be localized into a region of phase space smaller than 2 pi h bar cubed because of Heisenberg's uncertainty principle. So this is the size of a fundamental element. Wow. Therefore, the number of phase space elements in d3x, d3p is... Okay. All right. So they have another equation for that. Wow, look at how they're getting all this. This is so cool. This is so cool. They figured out even that. The fact that you can't go below a certain togetherness. The pressure can be, so they have a way to derive the pressure. I don't care anymore. Tonight they're they're getting the pressure by doing all this. Wow, Heisenberg, that German has done really well here. Oh, and then also they have the Bose-Einstein distribution for photons. Because if you say everything in terms of a temperature, you can actually, in equilibrium at temperature T, bosons such as photons have Bose-Einstein distributions. So you can, and fermions such as electrons have Fermi-Dirac distributions. So that's where the statistics comes in, and you can write down pressures and things like that. So that's why basically this T mu nu energy momentum tensor, having that rho for energy density and the P's for pressure, they're able to calculate all this with the fact that you have Heisenberg's principle, which means that you can't go smaller than a certain phase space, and also because photons are bosons and you can apply Bose-Einstein distribution to them, and the other things, if they're fermions, you can apply Fermi-Dirac distribution to them, which is the statistical distributions of those things. So at the end he's saying, although we have framed the argument in terms of a single species, this scaling holds for total entropy, including all species in equilibrium. In fact, even if two species have different temperatures, the sum of their entropy densities still scales as a to the minus 3. So long story short, the matter energy density goes as a to the minus 3, and the radiation energy density goes as a to the minus 4, where a is scale factor. And that is sort of the end of the math of this bit here, which is the math of the smooth universe. We kind of established, so we're done, at least with the math for now, because after this, the chapter basically has cosmic inventory, which we talked about earlier already. We talked about how the cosmic inventory is photons, baryons, dark matter, neutrinos, and dark energy, and how they proved that they need dark energy as part of the cosmological model in order to explain the evidence that we got from the supernovae data of the things, of the luminosity distances changing between the supernovae at different redshifts, which is explained by expansion of the universe. So we kind of looked at that already in the past live streams, but mainly this live stream I wanted to establish some of the math that keeps coming up. I know we didn't really do it super exhaustively because it's a lot of work, and I need a whiteboard, and we still haven't really established why we get 8 pi g, but we kind of got a little bit more familiar with some of the concepts. Scale factor small a, super important. Cosmic time t, super important. We had seen this equation for the Hubble rate, which is basically dA dt over a. That's a derivative of the scale factor with time, all divided by a. And because we saw this equation of the Hubble rate being related to the energy density of the universe, and we got this critical energy density as well. Later on, we saw how that all comes to be. We had to do a little bit of math, diving to see how general relativity works. It works with four dimensions for time, as well as 3 space dimensions. And the coordinate system works a little bit different than our Cartesian coordinate system, but has some of the similarities. For example, we saw the metric, which is the invariant of this, which is this matrix having certain diagonal elements and no non-diagonal elements, not now anyways, for the smooth universe's expansion. We saw the geodesic, which is basically the equivalent of a straight line for a free particle in the Cartesian coordinate system. And we saw how Einstein's equation is written down with the Einstein tensor equal to 8 pi g energy momentum tensor. And that energy momentum tensor is what gives you the energy density rho. So anytime we see rho, it's because of the energy momentum tensor. And Einstein, his equation basically gives us a simple way of writing down the universe's equation in terms of its energy momentum tensor, which is of course also a four-dimensional thing. It's a 4 by 4 matrix, the energy momentum tensor, because just like Einstein gave us four space-time dimensions, he also gave us four energy momentum things. It's kind of same, right? Space-time relativity and mass energy or energy momentum. It's similar type of structures, basically. But we also got introduced to the Ricci tensor. This is basically more to do with math, and Ricci curvature gives us a way to get back to the scale factor. And we saw how the Hubble rate equation that we initially saw is able to be derived from using that, like using the Ricci curvature math and getting A's out of it and then equating it to the energy momentum tensor side, which has rho in it. So that's how you can basically get Hubble rate related to the scale factor as well as the energy density. And you can even get a number for the energy density when it's critical. Critical energy density is given by all this. It's not too bad. It's given by 3h0 squared over 8 pi g. So now it should be, all these terms should be a little bit more familiar because we kind of saw how we get these. It's not easy math all through, but we have looked at a bit more detail how you get all these terms, how they all kind of come into the picture. So hopefully that's helpful. And also note, even though we did not look at every single detail of every equation, we're looking at it in a broad way. And the most important things we looked at: metric, geodesic, Einstein's equation, Hubble rate, scale factor. We kind of get it, right? Energy, density. These are all the important things. And on top of that, we also must note that we have now done this for the smooth universe. Like that metric g mu nu, small g mu nu, was a matrix that was 4 by 4, but only had the diagonal terms, right? So you can imagine that when we go into more detail later on, and we might look at perturbations, when people say perturbations around the smooth universe, you might see that changing. So for now, another way to think about the smooth universe is to say that, well, our tensors seem to only have diagonal terms. That's the math way of thinking about it. Isn't it nice when a matrix only has diagonal terms? Well, that's the case so far because we're considering smooth universe. So that's what's going on. Next, we will talk about beyond equilibrium and perturbations of the smooth universe. What time is it? 16% battery. Hi Peter, hi Ocean Waves, hi everybody. So basically, where this is going to be very important is when we consider, let me see where he actually goes to perturbations. I think it'll be why are you not? Oh, I think when we talk about cold dark matter, it'll be very important when we talk about hi Nazma J. Aymar, how are you? Hi, Nasma J. Um, so Boltzmann equation for baryons. So there's going to be some more equation solving later on. We don't have to do it in detail. I just wanted to make sure that our basic equations, we do understand sort of where they're coming from. We're not going to necessarily look at everything in an equation point of view unless we want to do that. I'm just looking for, where does he talk about, oh my God, where does he talk about the perturbation way of looking at cold dark matter? Is that not how it does? Okay, yeah. Freeze out is the inability of annihilations to keep the particle in equilibrium. Oh. I see. So, anyway, it's fine. Basically, it's an important thing that we looked at the smooth universe today and got all the equations that are important, at least for the most part, in understanding the smooth universe, because, when we consider perturbations to the smooth universe, then it's gonna be just that much more complicated. So it'll be good for us to understand. Hi, Levent Ostork. Then it'll be very important to start from that smooth universe. Oh, here it is. It describes the change in the photon momentum as it moves through a perturbed FRW universe. So yeah, if we didn't look at the smooth universe, then it'd be like, well, what do you mean perturbation? It's really adding complexity to what we just started with. So it's okay. It's all good. We will get there in a different live stream. Today we're just chatting at this time. We've just covered sort of the basic math of the smooth universe, and that's a great start. I see. I just was hoping that this author will give us so there will be some extra terms. That FRW metric, the G mu nu that we looked at, when we add sort of more terms to it and things like that, those will all have different types of significances and meanings, which we will discuss later on. But keep your mind open towards that going forward, kind of anticipate that going forward, because remember, so far we're just considering the smooth expanding universe, and pretty much we know that in the smooth expanding universe, the main thing is dark energy. It's 70% dark energy, 25% dark matter, and 5% ordinary matter. So, roughly speaking. And as far as understanding what is dark matter, we might have to look at more complications that are not captured at that zeroth order. So we'll get into that going forward. So this is sort of a preview of that going forward. Hopefully this was helpful. I need to charge my phone, but we can keep chatting. How's everybody doing? Hello. Thank you so much for joining. I forgot to take any clips, so I guess I don't have that. Oh yeah, some Legendre polynomials. You know what I don't understand is how dare he? He introduced the Ricci tensor. Like, we all know what that is. Oh. Oh. Mm. Oh my God. So, the other nice thing is, even though these things, there's a lot of dimensions, and so there's a lot of like terms, right? Right. Really, all of these are like G mu nu. There's a G00, there's a G01, there's a G02, G03, G1, one. You know what I mean? Like there's a lot of terms here, but depending on which exact term you're solving for, sometimes it becomes a little bit more simpler because of it being equal to something that goes away and etc etc, or sometimes it can be thrown away because it's not really anything significant in that order, you know. So we'll get into some of that stuff too going forward. I'm kind of seeing that stuff here. Page 121, two components of the Einstein equations. See, I feel like he has this is what it is. There is a whole separate chapter on Einstein equations. What did I name this live? I don't even remember. But basically, I probably could have come here. I'm just now noticing that he has a whole separate chapter on Einstein equations. It's chapter 5 of this book, and maybe here he gives us more definitions. So yeah, here he goes over it again. Christoffel symbols, Ricci tensor. We kind of saw the Ricci tensor a little bit, but not in as much detail. Okay. One second. So I think this chapter, it's going to be about the perturbations, so it's fine. I don't think we missed anything today. Basically, in this chapter 5 version of the Einstein equations, we basically get the perturbations, which we didn't care about for the smooth universe. So it's all good. The general relativity. Oh, apparently there's a book called Black Holes and Time Warps. I should probably get that and get a bit more of a mixture of history, science, and personalities. It's the best popular science book I've ever read. Wow. So apparently Scott Dodelson is telling us to buy a book. But we don't have to buy it. I'll just go get it from the library. Maybe I'll cover that here next time. You know what? Yeah. I'll mix up all this type of stuff, which is the more technical, more mathy stuff, with a little bit of science, like popular science as well. So the book we might look at is called Black Holes. I'm ready for a black hole, man. Who doesn't like black holes? Because black holes are not that bad. That's what's like nice about black holes. So Kip Thorne probably. So remember how Einstein's equations were solved exactly for the first time by Schwarzschild for a point-like star, and he called it the dark star or a black hole, like the singularity, and they thought that like black holes were so crazy and like you couldn't find them or something, but then actually black holes are totally a thing, and they're not that crazy. They're actual really real things, and we have discovered them and whatnot. So we will cover more on this. This will be cool because Einstein's equations get to be kind of they're kind of complicated, right? So it'll be a nice exercise to solving for black holes. That's what Churchill did. But at the same time, the context that we have been following up on here in these few live streams is about the expansion of the universe, smooth universe, and seeing that when you do all this math and you get the Hubble rate and you relate it to scale factor and energy density, and then you try to find the energy density contributions of the various energy components of the universe, it's basically we're determining all that and what even makes up the universe, right? So I think in this context, it's good that we covered all this because, I mean, Einstein did his general relativity in order to give us the math of the universe, right? Not just a black hole. So it's good. It's good what we have done today. Good job, guys. Everybody, thank you so much for hanging out and being on this live and coming on this math ride with me and the kitty cats. Ooh, here's Suji. She's been sleeping here this whole time. I think she came down. She was upstairs before. I promised kitty cats, and I didn't show as many kitty cats today because I was a little focused on the math and the equations. Thank you, everybody. Oh, I'm sorry I disturbed you. I'm so sorry. Oh. Little Suji mama. But yeah, hopefully you enjoyed this cosmology discussion. We will continue such things going forward. And indeed, we will cover more math and such. Well, we wanted to establish this math today, which gives us things that are the basic equations for the smooth expanding universe. But going forward, I think we will touch upon cold dark matter, and we will look at a little bit of the higher order perturbations of the smooth universe, just because that is so important. I believe in understanding something like dark matter and other such effects. So we will, to get the expansion and to understand dark energy, because that is most of the energy content of the universe right now, it was fine to just look at the smooth universe. But I think going forward, when we try to understand dark matter and its evolution since the beginning of the universe, we might have to delve into some of the higher order perturbations of this smooth universe that we talked about today. And so just remember that all of this math, we did it at a rough level, which is fine enough for describing the smooth universe. And we did a good job of understanding the basics that we saw with all the different terms and things like that, what everything means and how you kind of derive everything at a broad level. So that's what we covered today. But I think going forward, we'll cover something about cold dark matter, the cosmological view of dark matter, and we kind of established its importance already in previous live streams. So if you missed that, then feel free to go to the 2 or 3 live streams ago. We were talking about the cosmological viewpoint on dark matter. We probably touched on it on all of the live streams, for a few consecutive live streams. So I'm sure you can find that in the earlier videos here. But basically, we will come back. We will touch back on it, circle back to it with this new math understanding, or not new, this level of math understanding established already. We'll touch back on it. And then I think I'm going to find that black hole and warped time or whatever it was book, popular science book as well. If you have any suggestions, also let me know. Leave any comments once you see this as a video upload later on the channel as well. Thank you so much. Today we did a little bit of a math heavy kind of episode, just because I thought it was very important to establish this basic type of math now, so that because we will keep on referencing to it things like the you know, energy density, the critical density, the Hubble rate, the scale factor, cosmic time, G mu nu, the metric, especially the FRW metric, will come up again and again. So that's why I thought it was important to kind of establish it now and take a look at all of those equations and everything like that written out. So that's why we approached it this way for this episode. We might not look at all of the math in so much detail going forward. But whenever there is something really important, I'll show it to you. And yes, I still didn't really establish today where we get the 8 pi g from. I'll do some homework on my own and touch back upon that next time when we go live, which is probably tomorrow. So thank you again so much for being here. And I'm gonna put the phone over there now for charging purposes, and you can still be in the chat and ask any questions or make any comments. Thank you for being here. Bye bye. As in, I'll still be around, but bye bye to my face. Bye. Good night. See ya tomorrow, and we'll still be around for a bit. Thank you for joining. Bye, Peter. Bye, Nazmije. Bye, Levent. Hi to everybody who's joining. Okay. All right, let's charge the phone so that we don't die suddenly. Oh my God, my back hurts from sitting. Oh. Okay, there we are. Ooh, I usually tell you guys what we just read so that people understand, so we will do that. Hi, Baji. Don't disturb Suji. Give her some space. Oh, that's my hair. There. That is, wait. What is happening right now? Oh, here. I was like, why do I have to do it? Why is it difficult? It's difficult because I had to turn the camera. All right, guys. Also, I would really appreciate if you could like the live. Thank you so much. Please like the live, share, subscribe. And, you know, if you're joining, you can also go back in time to catch everything that we discussed today, which is a lot of the really basic math for cosmology and the smooth universe. So please do feel free to go back in time and check all of that out while we're still live. And thank you so much. Please do like the live so that we can get like 10 likes maybe, at least, or something like that. Oh. And this is the book we've been referencing for this live stream. So thank you to this author, Scott Doodleson, as well. Thank ya. So I can't see the live anymore on my other device. Ah, jeez. Once again, thank you everybody. Thank you for being here. I'm still around. Hi, everybody. I sleep so deep. Thank you. Always good to hear your voice. Thank you. Thank you, everybody. I'm about to go to bed, but thank you, everybody, for being here. Okay, babies, come. Come. We'll do a little snack. Come. Oh. My legs are so sore from working out. Oh my god. Okay. Hi. Just doing the last few things and then going to bed. Fuji Garna. say good night. Good night. Good night, says Baji. Good night from Suji and good night from me. Bye, guys. Good night. See you tomorrow. Bye. Go back into the live to see what we covered tonight.